Hi, my name is Víctor Elvira from University of Edinburgh, and today I'm going to talk about anti-tempered layered adaptive importance sampling. This is a joint work with Luca Martino from University Rey Juan Carlos I from Madrid, and David Luengo from Polytechnic University of Madrid. I want to thank the organizers of the special session, that covers intersection between MCMC and importance sampling, and also thank you to the organizers that have continued in organizing this nice workshop in these difficult circumstances. So I'm going to start introducing importance sampling, then I will cover adaptive importance sampling and present this layered adaptive importance sampling method and some extension related to it. So let me define the notation here in this slide. I put Bayesian inference as an example, but you know, importance sampling or MCMC are methods that not necessarily need to be restricted to Bayesian inference. Usually they can be used in order to simulate samples from some distribution or approximate integrals with respect to it. So the PDF is going to be this pi tilde, while this pi is going to be an normalized version. So pi tilde integrates up to 1, pi integrates up to z. This z usually it's an unknown normalizing constant, which in the framework of Bayesian inference, it's the marginal likelihood. I'm going to drop the notation here. From here to here, you see that maybe here I'm conditioning to the observed data. I will drop this, as I said, but you can think, for example, that this normalized version could be in Bayesian inference likelihood times prior, and this x, of course, is the space. It's defining the space of the unknown quantity, unknown vector, or latent variable. So importance sampling is going to help us to approximate integrals of the form. Sorry, I'm going back here to of this form with respect to pi tilde, the targeted distribution. This g is some moment, some function with respect to x. And the way it approximates this integral is simply by two basic steps. So in the first step, in the sampling, we obtain capital N sample from something that we call proposal distribution. We will dig into this very soon. Something you can choose, some PDF that you can choose. You simulate these N samples, and then you assign to each of the samples an importance weight. And this importance weight is only, is as simple as this. It's the ratio between the unnormalized version of the target divided by the proposal density, evaluated both at the sample here, okay? So once you have your N, capital N weighted samples, you can build estimators on this integral. This is the same as in previous slide, by this guy here, which is called the normalized importance sampling estimator, that you can use if you know the normalizing constant, or you can approximate the integral with the subnormalized importance sampling estimator, where you don't need this normalizing constant, which is very useful in many scenarios. And here, what you need to do is to take these N weights and normalize them in such a way that they sum up to 1. They are non-negative by construction, and they sum, the normalized version with the bar, they sum up to 1, okay? So this is a graphical description of the targeted distribution here, a bimodal PDF. This dotted blue line corresponds to the proposal PDF. And the vertical lines are correspond to samples that are simulated randomly from the proposal distribution, and the height is going to be proportional to the importance weight. Remember, target divided by the proposal. Okay, so how should I choose this proposal density? Of course, what I said before is valid. These estimators are valid, but for many choices of Q. But of course, I was saying we want a Q that is good in some sense. And usually what we refer is, the sense we refer is a Q that yields the a normalized importance sampling estimator or the self-normalized importance sampling estimator with low variance. Here I'm showing the variance of the unnormalized importance sampling estimator is this guy here. Again, I cannot solve this integral in order to characterize my importance sampling estimator, but I can tell you that the Q, if you can choose their proposal, the Q that minimizes this variance here is going to be proportional to this multiplication here. So this is the moment, absolute value, and this is the targeted distribution, okay? For example, for the normalizing constant, you wouldn't have G here. It would be only the integral of pi tilde, and the optimal proposal would be equal to the targeted distribution, to pi tilde. Here I'm showing you the same target distribution, or very similar than before in blue line. This is the bimodal target distribution. This is the proposal density. Here I'm choosing a kind of good proposal. It's centered at 0. This proposal has mean 0. While this proposal in red has mean -3. Again, I'm showing you here samples. Now I have many more than before. The height is still proportional to the importance weight. And what we observe here is that we get huge weights compared to this left graphic. Those huge weights correspond to weights that are going to impose a large variance on these estimators, okay? So this variability, I have here small weights, big weights. This variability in the weights is going to be responsible of a large variance of the estimators. So probably, or hopefully, I already convinced you about how important it is to have a good proposal. Usually you cannot get a good proposal in advance. Sometimes you can, but usually it's a very difficult problem. Remember that pi tilde can be only evaluated and actually up to a normalizing constant. Usually you don't know how much probability mass you are missing if you're exploring some area. This pi tilde could be multimodal, could be skewed, could be heavy-tailed. And it's, as I said, very complicated to choose a proposal a priori. So usually the strategy is to iteratively improve the proposal. So this is done with adaptivity, and then use several proposals. So basically with this sentence, I tell you that the two usual strategies in importance sampling is to have adaptive importance sampling and multiple importance sampling. What I'm going to present now combines both strategies, okay? So it combines both strategies because now we are going to have a set of n proposals. That's why it's multiple importance sampling. And they are going to be adapted over the iterations. So this index now n, this n here is going to be related to the number of proposals. And this index t in red, it corresponds to the iterations. So I'm going to start with a set of n proposals that are parameterized by this mu and this c. And then I'm going to go from iteration 1 to 2 to t, so on and so forth, okay? Note that here the mu has dependence with respect to t, while c does not. So what I'm doing here is that, okay, I have a parametric form of a proposal density. The mu's correspond to the parameters that are going to change over time, while c correspond to the parameters that remain fixed. Sorry, there's a typo here. This t should not be here. It's going to be like this. They are not going to be changed, okay? So basically the problem here is how I'm going to adapt the mu's, the parameters that evolve from 1 to 2 to every iterations up to the end of the algorithm. So let me present a generic algorithm of adaptive importance sampling. This necessarily does not cover every single adaptive importance sampling algorithm, but many of them, maybe most of them, have a similar structure that's summarized here. So we are going to have t iterations. That's why we iterate from 1 to t. N proposals per iteration, m samples per proposal per iteration. Then we initialize the n proposals. And then for each iteration, I will simulate exactly m samples per proposal. So I will have m times n samples at this stage. Then I have the weighting scheme. So note that first and second is like standard importance sampling. I will apply an importance weight assigned to each of these samples. Note that here, the structure is very similar to the one I presented before, pi, the normalized version of the target, but in the denominator, I'm plugging this function here, but for the moment, I'm not telling you what it is. And I'm not telling you what it is because there are several things, or actually many things, many functions that you could plug here, and still the importance sampling estimators would be valid, okay? I don't have the time in order to discuss this here, but if you're interested, I recommend this paper, Generalized Multiple Importance Sampling, where we explore these choices of not only of weighting, but also sampling and mechanisms, schemes of multiple importance sampling. And we show that there are not just, or there is not just one unique way of doing importance sampling once you have more than one proposal. And note something interesting here, we have more than one proposal in space, so we use n proposals, but also in time. One can consider that at the end of the day, you will use t times n different proposals, okay? And finally, as a third step for each iteration, you can, or you must adapt the parameters mu from t to t+1, okay? So there are basically two questions here in colors. The first one is how I am going to adapt from here to here. The second is how I'm going to weight. Here I'm going to talk more about the adaptivity. Again, I'm going to just cover one particular algorithm with some variants. If you're interested in having some survey, some overview of these adaptive importance sampling algorithms, I recommend this present survey and the Signal Processing magazine. So I'm going to focus on one particular adaptive importance sampling method, which is the LAIS, Layered Adaptive Importance Sampling Method. Note that this slide is very, very similar to the previous one. So we are going to particularize the two questions that I had before in the previous slide. So one question, remember, was what should I plug in the denominator? Among the many choices you could have here, you could plug, for example, for each particular sample, you could plug exactly its own proposal. But here we are plugging the set of proposals, so a mixture, equally weighted mixture of all proposals at iteration t. This is called the deterministic mixture weights, or the balanced heuristic weights. Are called differently in different communities. And in this paper that I mentioned before, we show that among the many different ways you can do the weighting scheme, this is, up to our knowledge, the best you can do. And there is some variance analysis, and for example, we can show that this is going to be always better, the normalized importance sampling estimator in terms of variance, that if you only plug here the corresponding proposal when you sample this sample. Okay, so this is the first question. And the second question, and maybe more interesting for this talk, is how I'm going to adapt the parameters. At this point, I'm going to consider that I have Gaussian proposals. It could be t-student, student t's, or it could be probably any other proposals defined in the Euclidean space, unbounded. I'm going to think more about Gaussian proposals because of for the sake of the explanation here. So this is going to correspond to the location parameter, so the mean of the proposal, and this is going to be, in principle, the covariance. Okay, the C is going to be the covariance. I insist it could be possible to think of student T proposals, but this is going to be the covariance here. So I'm going to run an MCMC over the location parameters of the proposals, okay? And then I'm going to adapt each of these location parameters. Let me show you how we are going to do it. We are going to use a Markov chain, and actually we're going to use a MCMC, Markov chain Monte Carlo algorithm, in order to obtain the new location parameter from the previous one. what is the advantage of doing this? I insist on this survey that I mentioned before. Maybe you can see different ways that you can do adaptation in general terms. Here, one of the advantages is that the process of generating the samples is decoupled from the process of generating the location parameter. So you are going to run an MCMC over here, and then we need to maybe choose, and I didn't tell you yet, what is going to be the stationary distribution of this MCMC here. I'm going to call it for the moment H of mu. Note that the space is going to be the same space as the space of X, because the location parameter is the mean, for example, of the proposal. And the challenge here, the degree of freedom, is the choice of H, okay? So let me show you one particular case that we have implemented in this paper. That there are several variants that we proposed here. I will focus on one, and then I will focus on one variant of it. So for the moment, I don't tell you what to do. This is just a summary of the same algorithm. So remember, we will simulate for each proposal, and at each time step, we are going to simulate from this H, we consider that the MCMC chain has converged, and then we obtain these mu's with a stationary distribution H. And then, condition to these mu's, I will simulate my samples. Remember, at the end of the day, what I want is have these samples, and then assign some importance weights. So it is interesting when you express this proposal in such a way, because it's a location parameter, because this H, it's going to be the prior PDF over the mean of this proposal. So what I mean by this is the following: if you're going to simulate mu that has stationary distribution as H after the Markov chain has converged, then you can see that the samples that you will finally simulate come from this equivalent Q tilde proposal distribution. So basically what I'm doing here is that I'm conditioning on mu of the location parameter, and then I marginalized mu multiplying here with the invariant distribution, okay? So what I want to show by this is that, okay, my samples are finally being simulated when the chain has converged from this proposal. Maybe a good question is what this Q tilde should be in order for my algorithm to be efficient. And maybe I would like that Q tilde is equivalent or is the same as the targeted distribution, okay? What I'm going to do here is just a way of putting this, equivalent operation in the Fourier domain. So basically, if you realize this is going to be a convolution, this is exactly a convolution of this function Q and the function H. And maybe you know that when you work in the Fourier domain, when you have the Fourier transform of this guy here, and this guy here, the convolution is going to be finally simple as a multiplication. So basically, if I know what is the optimal, in some sense, Q tilde, remember the equivalent proposal is pi tilde, I want to know what H should I plug here in such a way that this is equivalent to pi tilde. And basically in the Fourier transform is easier to put it, okay? Again, this integral is going to be, is not going to be analytic, and even when you work in the Fourier domain, this is not going to be possible. You're not going to be able to find this H. It's not going to be possible also because there's going to be an extra difficulty. I will show it right now from a different angle. So if we want H to be equal to the targeted distribution, basically, if you think about this, what I'm doing at the end of the day is that I can think, okay, first I will simulate all my mu's, because this process is detached from the sampling of the samples. And then, condition to the mu's, I will simulate all my samples. So basically, one can interpret that condition on the values of the mu's, I'm going to simulate from this equally weighted mixture of proposals, okay? So this is interesting. So here I'm going to use, as I said, maybe I said it very, very fast, I'm going to use H, the process in the upper layer, in the process where the MCMC is going to simulate my location parameters, the targeted distribution. So, and then once I do this, remember, I will use the proposal centered at those values. And then I will simulate from here, actually, the samples. So if you realize, basically, this can be interpreted as a kernel density estimator of the targeted distribution. Why? Because these samples mu's are simulated from the targeted PDF. And once I'm going to reconstruct this proposal, this is going to be close in some sense to the targeted distribution, because it's the kernel density estimator of it. This explains why the LAIS, in the LAIS we use this choice of H, has a good performance, because basically it's going to have a version of the target distribution if you have enough samples of mu, and then the chain has converged, the MCMC. But the tails of Q tilde are going to be thicker than the actual targeted distribution. Maybe this is a good feature for importance sampling. Remember that at the end of the day, we are going to simulate from here and then obtain the importance weights. Maybe this is good for importance sampling, but sometimes it might be that it's too thick. It's going to be, you're going to have broader modes than the actual targeted distribution, and the importance sampling method is going to lose efficiency, okay? So I'm going to, in order to tackle this little problem that might be an issue in some example, I'm going to present the anti-tempered LAIS, okay? So again, here I'm not showing you anything new, just remember, if I'm simulating my location parameters from this H, and then condition to this H, I build my proposal, then my proposed samples in this double layer process are going to come from this equivalent Q tilde. One can interpret that if you plug here pi tilde, this is somehow a low pass filter of this low pass filter perturbation of this pi tilde. So basically what you are doing is the effect we commented before. You are going to have a broader modes and thicker tails. This is the problem I mentioned before. Unless this is a delta, your Q tilde will be always a version which is going to be more spread out. Always, if you use here a pi tilde, by definition, on this operation here, on this convolution that you are here. So the idea of anti-tempered LAIS is as simple as this. Instead of choosing H, remember, the stationary distribution in the upper layer where the MCMC is simulating your location parameters, you will use pi tilde with an exponent of beta, okay? And we allow beta to change over the iterations. Beta is going to be a sequence of exponents that are going to grow. The algorithm we are going to start it, this anti-tempered LAIS, is going to be started with a beta that is less than 1. So actually it's a tempered version of the target. This is good for the upper layer because it's going to probably accelerate the convergence of the MCMC. It's going to be more spread out. This effect of having these different betas is discussed in Del Moral 2006 and the paper also of Radford Neal. And it can be shown that you can, if you have a sequence of targeted in this way, you can actually benefit from starting from a spread out version of the target and then start having something closer to the target. But what we do here, apart from integrating this into the framework of LAIS, is that at some point we allowed beta not to stay in equal to 1, so H with beta equal to 1 would be exactly the target, but it's going to grow. It's going to be grow above 1. So this is what we call anti-tempering. So this might be a bit complicated for the MCMC, but if you select the previous betas correctly, maybe it's not going to be that problem. We have seen already this good behavior. And the benefit of this is the following, and I'm going to the previous slide. Here we are going to have an anti-tempered version of the target. You can imagine something which is unimodal, but is going to be peakier when beta is larger than 1. And whenever you apply this convolution, this low pass filter, if you like to see it in this way, then if you select C and beta correctly, this Q tilde is going to be close to pi tilde. Okay, so this is the benefit of anti-tempering. The challenge is the choice of this sequence of betas and also the sequence of the CTs. Remember, this is the variance of the covariance of the kernel that you use to do importance sampling in the lower layer, okay? The intuition here is the law of total variance. So the covariance of this Q tilde can be seen as the covariance, can be expressed as the covariance of the upper layer plus the covariance of the lower layer, because the way they interact, because our upper layer provides a location parameter. So this is another way of seeing it besides the low pass filter perspective. So we say here that ideally this pi tilde and this Q tilde should be equal to the pi tilde. Sometimes someone might discuss that depending on which integral you're targeting with respect to this PDF, you might be interested maybe in another age, but we are trying to approximate as close as possible the targeted distribution with a set of proposals. This is, for example, for the normalizing constant and many other integrals you might be interested. This is usually a very, very good choice. Okay. The challenge, of course, is, as I said, is selecting these betas and these C's. So this anti-tempered LAIS, hopefully it was clear enough. It's a version of these LAIS whenever you are going to use in the upper layer, in the MCMC, not the targeted distribution, but a version that might be anti-tempered, might be an exponent larger than 1. Let me show you this example to conclude. We have a mixture of Gaussians in 2D. We have 5 Gaussians, and we are going to apply the LAIS here. So the green squares are going to be the initial location parameters, and the pink circles are the final location parameters. Actually, remember, this is nothing but having an independent MCMC with invariant distribution, which is going to be the targeted distribution. Remember, in LAIS, it's beta equal to 1. So H is equal to pi tilde. And we compare this behavior with some standard PMC algorithm, which is another adaptive importance sampling algorithm. Which is one or maybe the seminal paper of adaptive importance sampling. So it's a very, very interesting paper as well. Here you can see that at the end we cover all modes. Okay, so LAIS works nice. Here what I'm showing you is H. So basically I'm showing you a tempered or anti-tempered version of pi tilde. So this with beta equal to 1. This is the one that LAIS is going to target in the upper layer. But anti-tempered LAIS is going to start with a beta, which is very small. So this is going to ease the exploration for the MCMC. And then as long as you increase the beta, you will arrive to the beta equal to 1, and even you're going to anti-temper, so you are going to anneal the target distribution, which is very good for the reasons I mentioned before, and probably it's going to be even more explicit here. What I'm showing you here in the left, I have the LAIS algorithm, which is equivalent to the anti-tempered LAIS with beta equal to 1, okay? And if you have the location parameters that are distributed as the targeted distribution, and then you sample in the lower layer from a kernel, a Gaussian density, which has some C, some here, you have some covariance that is not going to be a delta, then whenever you do this convolution that we showed before, or even if you wanted to reconstruct what is the distribution where all these samples are coming from, I'm not showing you the samples, I'm showing you the location parameters, then the reconstruction would be this red line, while the blue line is the targeted distribution. So here I have a spread out version of the target, which, as I said, it might be not as problematic in some examples. It would be a loss of efficiency in any case, and could be quite dramatic for some examples, this loss of efficiency. While here in the right, I'm showing you the anti-tempered LAIS with beta equal to 4. So of course, I'm choosing here carefully the width of the kernels, the width of the proposals in the lower layer of LAIS, in such a way that since the MCMC is running over an anti-tempered version, so I'm not showing you here, but probably would be something way more pickier. But then I have in the lower layer some proposal that is going to have some variability. Then the reconstructed mixture where all samples are simulated from can be very, very, very close, as you can see here, to the targeted distribution. So just to conclude, I have here some numerical examples where we compare different adaptive importance sampling methods. We can see the nice behavior of LAIS and even better of anti-tempered LAIS. I will not go into the details of these other methods here. You have more details, and I insist, maybe if you're interested in adaptive importance sampling, I recommend this reference here, the last one. And just to conclude, remember that adaptive importance sampling aims at approximating integrals, but also as a byproduct, it approximates the target with a mixture of proposals, okay? So LAIS is a hierarchical layered process that helps to explore the space, and then once you find good place, you place your proposal and then you simulate from there. If in the upper layer you simulate the location parameters via an MCMC from the target distribution, this is going to be probably reasonable. That's why LAIS obtains a very good performance in general. But in some cases, it could be maybe a bit of a waste of efficiency, because in the lower process, once you place the location parameter, the proposal there, you're going to have more variability, and then you're going to simulate from a broader, thicker tails, more spread out version of the target. So this anti-tempered version that I've showed here, anti-tempered LAIS, helps you to fight this behavior, and while keep having a good exploratory behavior. What I say is that the pros of LAIS is that it requires very, very, very few tuning. Anti-tempered LAIS, it can get a better performance, much better in some examples, but at the cost of having to tune the sequence of betas and the sequence of covariances of the lower process. So thank you very much for your attention. And if you have any question or anything you want to discuss, you're interested in adaptive importance sampling or on these particular methods, please write me an email, and I will be delighted to discuss more on this. Thank you again. Bye-bye.